Hello everyone. In today's video, I am going to discuss about how to solve the knapsack problem using branch and bound. Now to understand what do you mean by branch and bound, I would suggest you to go and watch my previous video wherein I have solved the assignment problem using branch and bound. But note that even in case of branch and bound, as similar to that of backtracking, we construct the state space tree, and with the help of the state space tree, by traversing it in both the BFS way as well as the DFS way, we find the optimal solution. Now coming to the knapsack problem, we know that in case of the knapsack problem, the inputs to the knapsack problem are the number of objects denoted with n. I have taken one such example wherein n is equal to 4, and with each of these objects, the objects will be associated with weights denoted with W, and each of those objects will be associated with profit or values denoted with V. Now, what is the objective? Objective of the knapsack problem is I need to place some objects onto the knapsack which has a maximum capacity. The maximum capacity of the knapsack is denoted with capital M, and I need to get the maximum profit on placing those objects onto the knapsack. Now what was the condition? Condition is the summation of weights of the object placed on the knapsack should not exceed the knapsack capacity. So this was about what do you mean by knapsack problem, what are the inputs to the knapsack problem, and what is the objective of the knapsack problem. So I have mentioned that the objective of the knapsack problem is to maximize the profit. Now as my object is to maximize the profit, it is a maximization problem. As it is a maximization problem, the bounding function have to be an upper bound. But whereas in case of the assignment problem, it was a lower bound. So note that in case of assignment, in case of the knapsack problem, it has to be an upper bound function. Now, one more important thing in case of solving the knapsack problem using branch and bound technique is all these objects should be arranged in such a fashion such that, if you see here, we should always order the items in the ascending order of their profit to weight ratio. Now when I calculate the profit to weight ratio of the objects, it should always be in descending order. In case if they are not in descending order, I need to rearrange the objects in such a way that its profit to weight ratio should be in descending order. Now let's calculate the profit to weight ratio. For the first object, it is 40 divided by 4. Now 40 divided by 4 is 10. Next, 42 divided by 7. See it is V1 divided by W1. It is always profit divided by weight. Hence it is profit to weight ratio. 42 divided by 7. 42 divided by 7 is 6. Next, 25 divided by 5 is 5. 12 divided by 3 is 4. Now in this example that I have considered, if you note, the profit to weight ratio are in descending order. This is there in the descending order. This is one of the conditions that is must before solving the knapsack problem using the branch and bound condition, using branch and bound technique. If they are not in descending order, then I need to rearrange the items as well as the profit in such a way that I get the profit to weight ratio in the descending order. Now once you are done, now you can start constructing the state space tree. Now as I told earlier that this is a maximization problem, I need to find the upper bound. I have denoted the upper bound as UB, and the upper bound for the knapsack problem can be calculated using this particular formula. That is V plus M minus W multiplied by profit to weight of the next object. Now initially I have not placed any of the objects onto the knapsack. So initially my V and W will be 0. Initial, that is so initial UB, that is the upper bound. What is this? This is 0 plus M. M is the knapsack capacity, 10 minus W. W is 0. because I have not considered any object, multiplied by profit to weight of the next object. Weight of the next object in the sense it is the first object. It is 10. So how much this is? This is 0 plus 10 into 10. It is 100. Please note that the initial upper bound value is 100 when V is equal to 0 and W is equal to 0. It means when V is equal to 0 and W is equal to 0, my initial upper bound value is 100, and this is the formula that I am supposed to use to find the upper bound. Now this was the initial upper bound value that I need to store it in the root node, and then I will consider each of the object, and then I will complete the state space tree, and with the help of the state space tree, let's try to find what is the optimal solution to this particular knapsack problem. Let's construct the state space tree to solve this knapsack problem. Now as we have already calculated the upper bound, note that with the value of W equals 0 and V equals 0, the upper bound calculated was 100. And as I told earlier, please note that all the weights should be in an order such that the profit to their weights should be in the descending order. In case if they are not in descending order, you need to arrange the items in such a fashion that their profit to weight should be in descending order. Anyway, in this case, as they are already in descending order, I have already calculated the upper bound. I have calculated the upper bound, and the upper bound value was calculated with this formula, which gave me 100. Now, why I need to arrange in ascending order of their profit to weight is because if I place the first object after reordering, I should get the maximum profit. In the sense, I should get the maximum profit on placing the first object, and I should get the lesser profit on placing the last object. Now, I need to proceed this state space tree. So, let's proceed with, we know that either we can place the object or we can discard the object. So, I'll have two branches with first object, without first object. Now, what is with object? First object, I should consider the first object. What is the weight and the profit of the first object? So, if you see, W equals 4 and V equals 40. Calculate the upper bound for this. Now, how to calculate the upper bound? W equals 4. Now come to this, and V equals 40. So this equation is 40 plus M minus W. M value is 10. 10 minus 4 into weight by profit of the next object. Weight by profit to weight of the next object is 6 into 6. So this is 40 plus 10 minus 4 is 40 plus 10 minus 4. 10 minus 4 is 6. 6 into 6 is 36. So 40 plus 36 is 76. So this is 76. Now without first object, my W will be 0 and my V is equal to 0. So what will be this? This is 0 plus 10 minus 0 into weight, profit by weight of the next object, that is 6. So this is 10 minus 0 is 10. 10 into 6 is 60. So upper bound is 60. Now among these two, which is having a higher upper bound is this node, which is a node with upper bound 76. As this is maximization problem, I should proceed with this node. Now continue further. This is with second object, and this is without second object. Now with the second object, if you see, what happens to W? W is 4 and weight of the second object is 11. 4 plus 11 is 4 plus 7 is 11. Whether your knapsack can hold 11 kgs, your knapsack can hold only 10 kgs of weight. So as 11 is greater than 10, this is not feasible. So this is a non-promising node. This is not feasible. Or I can say that this is a non-promising node. Don't proceed with this node. Now come to this. What it says, W is, this was without second node. Without second node, my W remains as it is, and my profit also remains 40. Now calculate the value of the upper bound. Now the upper bound value is how much? V is 40 plus 10 minus 4. 10 minus 4 into profit by weight of the next object, that is this. Profit by weight of the third, that is 5. So this is 40 plus 6 into 5 is 70. Upper bound is 70. Please do compare this upper bound with this upper bound. Okay, this is 70 which is greater than 60. I need to proceed with this. This is inferior when compared to this node. So I am proceeding with this node. So I have 2 more branches with third and without third item. Now with third item, what happens is this is your W will be 4 plus 5 which is 9, and my profit will be, what will be your profit? It is 9 V plus 40 plus 25 is 65. Find the upper bound. Now check this, what happens for this? It will be V is 65 plus M minus W. M is 10 minus 9 is 1 into weight and profit of the fourth object, it is 4. So 65 plus 4 which is 69. So this is 69. Now calculate this. This remains as it is. W is equal to 4 and V is equal to 40. Find the upper bound. It is 40 plus 10 minus 4 into 4. So this is 40 plus 6 into 4. 24 plus 40. 40 plus 24 is 64. Now see here, I have this node, this and this. Now which is having a greater upper bound is this node. So I need to proceed with this particular node. So continue with this. This is with fourth object and this is without fourth object. Now with fourth object, weight is 9. 9 plus 3 is 12. So W equals 12. So this is not feasible. Now this one without 4, W is 9 and V is equal to 65. Now what is my upper bound? I need to calculate. This is V is 65. 65 plus 10 minus 9 into weight to the profit of the next object. If you see here, this is already the fourth one. Next object, I don't have any object, so it is 1. So this is 65 plus 1 is 66. Upper bound is 66. Now, among the 66, 64 and 60, which has the higher upper bound? It is this node. It is this node. So, after fourth item, I don't have any other item. So, it should stop here. It should stop here. So, to get this upper bound of 66, what are the objects that I have included? See here, this is first object. Second object is not there. Third object is there. And fourth object is not there. So, what it implies? It implies what is the maximum profit? Maximum profit is 65. That means for this given problem, max profit is 65 and the objects to be placed are first object, first and third object. This is how we solve the knapsack problem using branch and bound. Hope this was clear. Thank you.